Temperature and solubility. Look at the data for cadmium iodide. At 20 degrees Celsius, 86.2 grams will dissolve in 100 milliliters of water. If the temperature is raised to 80 degrees Celsius, 126 grams will dissolve in 100 milliliters of water. In general, solubility increases with increasing temperature. But there are exceptions. Solubility does decrease with increasing temperature for sodium sulfate and cerium sulfate. Let's look at how oxygen gas solubility reacts to temperature. Solubility usually decreases with increasing temperature. This is true for most gases. The solubility of a gas in a liquid is proportional to the pressure of the gas over the solution. This is known as Henry's law. C is the concentration of the dissolved gas, P is the pressure of the gas over the solution, and K is a constant for each gas that depends only on temperature. In general, the concentration equals the constant times the pressure. Low pressure, low solubility. High pressure, high concentration, high solubility. Colligative properties of non-electrolyte solution. Colligative properties depend only on the number, not on the nature of the solute particles. The first is the vapor pressure lowering. P1 super zero is the vapor pressure of the pure solvent, and X1 is the mole fraction of the solvent. Raoult's law states that the pressure is equal to the mole fraction times the vapor pressure of the pure solvent. If the solution only contains one solute, then the vapor pressure lowering, delta P, equals the mole fraction of the solute, X sub 2, times the vapor pressure of the pure solvent, P1 super zero. Boiling point elevation is another colligative property. Notice that the solution always has a higher boiling point than the water, the pure water. The change in the boiling point equals the boiling point of the solution minus the boiling point of the pure solvent. Boiling point of the solution is T sub B, boiling point of the pure solvent is T sub B super zero. The change in the boiling point equals the boiling point elevation constant K sub B times the molality. Remember that the molality is the number of moles per kilogram of solvent. Notice for freezing point depression, the freezing point of the solution is less than the freezing point of the pure solvent, in this case water. The change in the freezing point, delta T sub F, equals T super zero sub F minus TF. Again, the super zero indicates the pure solvent, the freezing point of the pure solvent, and T sub F is the freezing point of the solution. The change in the freezing point equals the freezing point depression constant, K sub F, times the molality. Here's a table of molal boiling point elevation and freezing point depression constants for some common liquids.